The knowledge sharing will not only improve our teaching, but also gives great benefits to the students and society. Hope this FDP program would be helpful to you all to enrich our knowledge as well as helpful for everyone. It's my pleasure to introduce today's speaker for today's session, Dr. Sauram Mondal. Welcome you, sir.
Good afternoon.
He has completed his PhD from the National Institute of Technology, Durgapur, India. His research interests include chemical graph theory, spectral graph theory, and fuzzy graph theory. He is currently working with Professor Kinkar Chandra Das as a postdoctorate fellowship in the Department of Mathematics, Sunkin-yon University, South Korea. He is also serving as an assistant professor in the Department of Mathematics, SRM Institute of Science and Technology, Kottankulathur. He has published 30 plus research publications in both national and international journals. We are very proud to welcome you, sir. Welcome,
Thanks.
sir. Yes.
Thanks for the nice introduction.
Thank you, sir. You can start your presentation.
Okay. Thanks for giving me the opportunity to share my knowledge about chemical graph theory and its applications. This is the overview of this talk. We'll start with the history of graph theory. This is a famous Königsberg problem. Königsberg problem. This is the city of Königsberg, which was formerly in Germany. Now it is in Russia. The city is divided into 4 land areas by the Prizren River. The land masses are connected by 7 bridges. There was a challenge that starting from any landmass, is it possible to cross each bridge exactly once and come back to the starting point? This problem is known as the famous Königsberg bridge problem, and this is the graphical model of the problem. And this problem is considered to be the origin of graph theory. So what is graph? It's a mathematical model of almost any real-world problems involving discrete objects and relationship among them. It can be considered as an ordered pair V, where V is the vertex set and E is edge set. The degree of a vertex is a certain kind of graph parameter, and it is defined as number of nodes connected to the vertex V. The distance is also another parameter, and the distance of 2 vertices is the length of shortest path between them. This is the pathway in which the graph theory is developed. These are few among the vast area where graph theory is applied. One such applicable area of graph theory is the chemical graph theory. Basically, it's a branch of mathematical chemistry that connects graph theory and chemical sciences by means of molecular graph. A molecular graph usually represents the structure of a molecule, where nodes correspond to atoms and edges correspond to chemical bonds between them. For instance, this is a chemical structure of propane, and it is corresponding molecular graph. Here, nodes represent atoms and edges represent chemical bonds between them. Now we explain about molecular topology. So consider a molecule M containing n atoms, A1, A2, A3 up to An. Now let Ai and Aj be 2 arbitrary atoms. Now they may be chemically bonded or not. Enter information regarding the mutual connectedness of all pairs of atoms in a molecule, and only this information describes the topology of the respective molecule. Thus, a molecular graph represents the topology of a molecule by considering how the atoms are connected. So this is basically related to connectivity problem. The topology of a molecule is essentially a non-numerical mathematical object. On the other hand, various measurable properties of molecules such as boiling point, entropy, enthalpy, eccentric factor, all these are usually expressed as numerically. To connect a molecular topology to such molecular properties, the information contained in the molecular graph must be converted into numerical aspects, and the topological index makes such conversion. It is a numeric quantity generated from molecular graphs by some algorithms, which characterizes the topology of the molecular graph.
There are also software like treatment and details. No fingerprints, no electronic.
Since it explains different properties of molecules, it is
Hello, sir. You can mute and unmute once again, sir. Sir? Sir, Saurav, sir? Saurav, sir?
Sir, your mic is in mute.
Saurav, sir? Dr. Saurav, sir, you can mute yourself and unmute once again, sir.
Is it okay now?
Yes, sir. Yes, sir. Thank you so much.
So a topological index can be considered as a numerical graph invariant. It can be mathematically thought as a function from the collection of all molecular graphs to the set of real numbers, such that it remains untouched under graph isomorphism. This idea was initiated in 1947 when chemist H. Wiener introduced the Wiener index for searching boiling points of alkenes. Although this journey was started in 1947, but the term topological index was first coined in 1971 when Hosoya presented the Z index. To investigate the structure dependency of pi electron energy of conjugated hydrocarbons, Gutmann and Tinanjistick proposed the Zagreb indices in 1972. Later, in 1975, Randick introduced the Randick index. There are numerous types of indices based on different graph parameters, including degree, distance, eccentricity, graph spectrum, and so on are defined, and some well-known distance-based indices are reported here. This is Hyperwiener index, Error index, Skulls index, modified Skulls index. These are all very useful distance-based indices, and actually they are defined on the distance between two vertices. That's why they are distance-based indices. Most of the degree-based indices for a molecular graph G are of the form summation F, where summation runs over the edge set, and F is explained in the following table. For different F, different types of degree-based indices are obtained. For instance, if f is x plus y, we get first Zagreb index, which is usually denoted by m1. Similarly, for x square plus y square, we get forgotten topological index. 1 by root xy, we get randic. Similarly, we get for varying f, we obtain different types of degree-based indices. The spectral graph theory can be thought of as an approach to use linear algebra, including, in particular, the well-developed theory of matrix for unlocking 1,000 of secrets about graph theory and its applications. One of the important tools in this area is the adjacency matrix, which is formulated as age equals to aij, where aij is 1 if there is an edge connection and 0 otherwise. Since ag is real and symmetric, its eigenvalues lambda 1, lambda 2 up to lambda n are also real, and they can be arranged in non-increasing order. The collection of these eigenvalues is called graph spectrum, where lambda 1 is known as spectral radius, and the difference lambda 1 minus lambda n is called spread. There is a close correspondence between graph spectrum and pi electron energy of conjugated hydrocarbons. Pi electron energy of conjugated hydrocarbon is n alpha plus beta into summation mod lambda I, where lambda is are the eigenvalues of molecular graph G. Here n alpha beta are constants, and the summation term is the only non-trivial quantity. In 1978, Professor Ivan Goodman named this quantity as graph energy. It is considered as a spectrum-based topological index, graph spectrum-based topological index. And a significant amount of works have been developed on the chemical importance and mathematical properties of graph energies. Inspired by this concept, a considerable number of graph energy-like variants are appeared in the literature by appropriate modifications of so-called adjacency matrix. These are some energy variants. Laplacian energy is very famous. Randic energy, inverse sum index energy, sum connectivity index energy, arithmetic geometric, atom bond connectivity, Jacob energy, and so on. Polynomials in chemical graph theory. Topological indices can be computed by their usual definitions, which is very laborious and time consuming, while one intends to generate many indices of a certain category for a given family of graphs. So instead of going through this time consuming process, one can use a compact general methodology related to polynomials to determine the indices for a certain family of graphs. For instance, the Hossoya polynomial, which gives the numerous distance-based indices actually. The M polynomial is the most general polynomial to produce a large number of degree-based indices. So these are some basic components of chemical graph theory. Now we are going to discuss some of our contributions to chemical graph theory. Its motivations are as follows. The QSPR analysis, quantitative structure property relationship analysis. Synthesis and characterization of compounds for drug design is like finding a needle in the haystack. It is usually very costly to test, to examine a compound using wet lab. It's costly as well as time consuming. But the quantitative structure property relationship analysis, that is QSPR analysis, allows that cost to be diminished, to be reduced. So basically, it's important to develop QSPR models, and development of predictive QSPR models plays a crucial role in the design of purpose-specific fine chemicals, including pharmaceuticals. The QSPR analysis actually links a set of independent variables to a certain properties or activity of a molecule. And the descriptors having the strongest correlation in this study give information about essential functional groups of compounds under consideration. And accordingly, we can maximize the beneficial effect and minimize the unwanted side effects of chemicals, including toxicity. Consequently, the pharmaceutical industry contributed to the increased interest in molecular descriptors, so-called numerical topological indices, because of the necessity to reduce the expenses connected with synthesis of medicinal drugs. Since the early 1970s, numerous indices have been proposed in the literature. However, there has not been any index that meets all the requirements, such as being unique for each and every molecule, easy to calculate, applicable to all types of molecular structures, correlating as many properties as possible, and so on. As a result, in addition to investigating well-known useful indices, novel indices that are more important, more significant from application and theoretical point of view than the existing ones must be developed, must be generated. So we define here a parameter known as neighborhood degree sum of a node, del G Vi. It is defined as degrees of all vertices connected to the vertex Vi. That is degree sum of all neighbors of Vi. It is the neighborhood degree sum of the node Vi. A significant proportion of topological indices research focuses on investigating their role in quantitative structure property relationship analysis and quantitative structure activity relationship analysis, as well as isomer discrimination. Evaluating different bounds with characterizing external structures, finding explicit expressions for various graph operations, and computing indices for useful networks. Researchers are performing such works for degree, distance, and graph spectrum-based indices. However, the neighborhood degree sum-based indices and corresponding energies are largely remained unexplored. These issues are emphasized in our contribution, and some research questions are raised here. look at an interesting feature of topological index, the spectral property of Ni, and it is investigated by modifying the adjacency matrix as gamma g equals to Aij, where Aij is del I del j by del I plus del j if there is an H connection, 0 otherwise. Here rho 1, rho 2, rho n, this collection is considered as the gamma spectrum. And in accordance with the general concepts by which the original graph energy idea is adapted to different graph theoretical matrix, the neighborhood inverse sum index energy, that is ENI, is also defined as summation mod rho I. The inverse sum index energy was first presented in 2018, and some mathematical study of that energy was later performed. However, no attention is paid to investigating the role of inverse sum index energy, that is EISI, as a regulator of molecular properties. That's why here we aim to examine the acceptability of EISI as well as ENI as potential structural descriptors. Unfortunately, no notable correlation is found for both the energies. To enhance the skill of these energies in explaining physicochemical properties, we devise a linear model EISI plus KENI, where K is a fitting parameter. And these figures reveal that the individual contributions of EISI and ENI in predicting different physicochemical properties are not satisfactory. But their linear combination reaches soft maximum. These are some structure property relationship for the linear model, where E pi is the pi electron energy of conjugated hydrocarbons. And this is external validation of the model. Here both the energies exhibit a very well isomer discrimination strength, having the sensitivity value 1, that is maximum. Now we would like to discuss some mathematical attributes of gamma spectral radius and Ni energy. The characteristic values of gamma g, except rho 1, are same only when G is complete or complement of Kn. This is an upper bound of rho 1 which attends on the complete graph Kn, where n is the order of the graph G. It gives lower and upper bounds of rho 1, where extremal graphs are star graph and complete graph. Here capital delta is maximum degree, small delta minimum degree, and small n is size of the graph. These are some crucial upper and lower bounds of the Ni energy with characterizing extremal graphs. This contribution was published on the Information Sciences Journal. a graph energy variant corresponding to the third version of Zagreb index, which is formulated as summation del GU plus del GV, where summation runs over the edge set is proposed here, for which the usual adjacency matrix is modified as omega g equals to del I plus del j if there is an edge connection and 0 otherwise. Here, similarly, eta 1, eta 2, eta n forms the omega spectrum. Analogous to the classical graph energy, the neighborhood fast Zagreb energy is defined here as nz1 equals to summation mod eta I. And to measure the degree of protein folding, Estrada defined the Estrada index in case of classical graph energy. Similarly, we formulate here the Estrada index of nz1 as summation e power eta I. We investigate the chemical connection of JD1, NJD1, and their Estrada indices. The performed statistics conclude that the Estrada indices can model density, molar reflection, and molar volume of octanes. On the other hand, JD1 and NJD1 can predict boiling point and pi electron energy of benzenoid hydrocarbons. This is a correlation matrix, so it yields that NJD1 is more distinct than JD1, which enriches the objective of including NJD1 in the spectral graph theory. Also, the current energies and their Estrada indices outperform the already existing well-established indices in isomer discrimination. Two structures having the same omega spectrum are said to be omega co-spectral. Otherwise, they are known as omega non-co-spectral. Graphs with the same NZE1 energy are known as omega equi-energetic. Now, it is clear that omega co-spectral graphs are always omega equi-energetic. But our interest is to characterize the graphs that are omega non-co-spectral but omega equi-energetic. Here we have identified the graphs that are omega non-co-spectral but omega equi-energetic. These are some crucial bounds of the Estrada indices, where N0 is the count of 0 omega ion values and NP is positive ion values. This is the integral representation of NZD1 for general graph, where theta I is matching of size I. Results can be obtained by using Cauchy residue theorem and contour integral. And this is the integral representation of NZD1 for the class of all tree graphs. Some more graph energy variants are proposed here, for which these metrics are defined and performed statistics and sensitivity analysis reveal that each energy can be useful in quantitative structure property relationship analysis and quantitative structure activity relationship analysis, and also isomer discrimination. An upper bound of the spectral areas is computed here, where the extremal graph is complete graph. These are upper and lower bounds of spread with characterization of extremal graphs. His contributions were published in the Chemometrics and Intelligent Laboratory Systems and Match. Future directions. So we have investigated the chemical significance and mathematical features of some newly proposed neighborhood degree sum-based invariants. Although our comprehensive study generates answers to various questions, many issues still remains unexplored and require further investigation. Some of these concerns are addressed here. So we have established the chemical significance of the novel indices and graph energy variance employing octane, decan, nonene isomers, alkanes, and benzenoid hydrocarbons. So this empirical study is expected to perform on other datasets, including aromatic, heteroaromatic amines, polychlorobiphenyls, polyaromatic amines, hydrocarbons, chemical free isomers, and so on. The integral representation of the present energy variant are reported here, whose implementations can be thought of as a future work. All such works has focused on Cripps graphs, which are deterministic and precise in nature. However, many real-world situations involving uncertainty are very hard to model using the Cripps concept. The fuzzy structure, fuzzy graph is a generalized concept of the Cripps graph to deal with such uncertainty, such vagueness. Therefore, the study of graph invariance in the realm of fuzzy graphs is significant, and it will be interesting to investigate the impact of current indices and energies in an uncertain environment. Some recent works on random matrix theory suggest that topological indices and the well-known random matrix theory can be helpful in the study and characterization of random matrix models. The investigation of the present indices for random networks, including Erdős-Rényel networks, random geometric graphs, bipartite random networks, and so on, is thus a direction for future work. These are some important references in the field of chemical graph theory and its applications. Thank you. Thank you very much for your attention. Any question?
Thank you. Thank you so much, sir. Participants, if you have any doubt, kindly interact with Dr. Sauru, sir. Participants, if you have any doubt? Dear participants, otherwise you can put into the chat box. I will convey to sir. Okay, sir. Sir, thank you so much for your wonderful presentation, sir.
Okay, thank you.
Now I call upon Satya ma'am, Assistant Professor, Department of Mathematics, to deliver the vote of thanks.
Good evening. Ma'am, my voice is audible?
Yes, ma'am.
Okay. Good evening, one and all present here on this wonderful evening. I would like to present vote of thanks on the behalf of the organization, Department of SNH. I take this golden opportunity to thank the respected chief guest of last day of FDP, Dr. Saurav sir. Thank you so much, sir. Well authorized speech. You really motivated us, gain to more and more knowledge about chemical graph. Thank you so much, sir. Next, I would like thank our beloved principal, head academics, head of SNH, Ammu Kudzia ma'am, Sudha ma'am. Thank you, ma'am.
Thank you, ma'am.
Next, I would like to thank our all the staff members and the technical staff. Thank you all. Last but not least, I would like to thank all the participants. Once again, I thank one and all present here. Thank you.
Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, sir.
Thank you. Thank you very much.
Thank you so much, sir. As your busy schedule, you can accept our invitation to give a nice presentation, sir, with our chemical graph and its applications. Thank you so much, sir.
My pleasure, ma'am. It's my pleasure.
Thank you. Thank you so much, sir. Thank you, sir. You can leave the meeting, sir.
Okay. Thank you.
Okay, I will call you later, sir.
Okay.
Thank you. Thank you. Thank you, dear participants. Thank you for cooperation for all the days. Kindly fill your feedback form and also certificate form. We can dispatch the certificate within 1 week. Kindly be patient because we need some time because we are busy with our schedule, right? So kindly give us for 1 week time to dispatch the certificate. Thank you. Any other feedback regarding the conducting of FDP? Any other feedback means or any other issues means you can just tell me. Always welcome. Anybody is in willing to tell the feedback about FDP? Today you have to fill both feedback link and certificate link and then leave the meeting. Thank you all once again. Thank you for your cooperation. Thank you so much.
Thank you. Thank you.
Thank you, sir. Thank you. Sir, PPT is not available with us. YouTube streaming is available. So I already shared the YouTube streaming videos and all in our WhatsApp group. Okay. So if resource person provided PPT, I will share definitely to your registered mail ID. Thank you. Thank you all once again.